we'll be talking about a project which was on sorting networks. The problem is, given a set of input numbers, we wish to sort them. The already existing parallel network is the bitonic sorter, and it uses the input of the form 2 power k, and it has these many number of comparators. Now our problem is to design something better than this for at least one given value of n. And our target is only to reduce the number of comparators that are being used in total. Now we'll start by looking at the phi sorter. If you look at note, it shows a version of the phi sorter that uses 7 comparators. So this is the problem given. You're given 5 numbers, say A, B, C, D, E, and you have to put them in a sorted order. So what note does is, we first start with any two pairs. So you take A, B and C, D and you compare them. So without loss of generality, we can assume that say A is less than B and C is less than D. Then as a next step, we look at the greater numbers in these two, B and D, and we compare them. So for now, let us assume that B is less than D. So at this point, with 3 comparisons, we have this particular order. Now we wish to insert E into this part. We can do this by using a binary search.
Oh, this is clear.
Right, so here we'll use 2 more comparisons, and for C again we'll use 2 more comparisons. So the total becomes 7. But the problem in this one is that it uses 6 phases, the one that Note has. It's a sequential algorithm. So what we are going to do is we'll improve that design first. We will reduce it to 4 phases, but the cost is we'll be using 1 more comparator for now. So what we'll do for that is the starting part remains the same. 4 parallel phases.
Okay.
So for now the first phase still remains the same. We shall compare A and B, C and D, and then the greater of these two. So again, now our task is to insert C and D into this. At this point what we do is we compare C and D. This will be done in parallel with B and D. So because there is nothing common, we can compare these two. So now based on the result of C and D, we get 4 cases in each of them. We get a total of 8 cases, and I'll just show that in the worst case it takes 4 comparisons and 2 phases extra after this point. So at this point we have 4 comparisons, and these both happen in one phase, this and this happen in another phase. So we will use a total of 4 phases and 8 comparators for this. These are the cases here. Well, I'll talk about the worst case that exists. In the worst case, we have C is less than E. C greater than A. B less than E. So you can see that since C is greater than A and less than D, we have even C less than D. To put C into its right position, we need to compare C and D. So that is the first comparison that we'll do. And for E, we see that E is greater than C, and so in that case we'll compare E with D. For C we need C and D, and for E we need E and D. So with these two comparisons we'll be able to put C and D into the right positions here. And we already know what happens between C and D, so we can put the entire phi sorted together. So this is where we have 4 comparisons and 2 phases. This is a case-wise analysis. So do you want me to go through them? Or?
No, you just show me the network-wise how it works.
Okay.
You put 5 dots or ABC.
I'll just put ABC. This is the first phase, sir.
B is compared with?
In the second case, sir?
The second is B is compared with D.
A, B and C, D is the first one, second is B, D and C, E. So B and D are the larger ones. And then we take C and D. This is the second phase. For third phase, now we do B, D and C, E. Based on this result, this will be our third phase. So. Fourth phase is only in the worst
You
case. So we
You
will
are
be doing
computing?
BDC.
B and C. Okay. Four.
So this is the second phase. So BD and C is the second phase. The third phase is this is the third phase. So in case of this, we go for this. In case of this, we go for this.
No, but you interchange it, right? So you always get
Right?
uh,
Yes, we get the smaller one with A, whichever is smaller.
no, whichever you draw that, then only I will be able to understand the diagram. Now you get
Now we take right, sir.
A is smaller.
A is here,
This is minimum.
right, and this is going with a minimum of C and D. Sir. We compare C and D
So
here.
this diagram you have to give me.
Okay.
Otherwise, all those cases,
Okay.
this is the things I need.
I thought we'll put it case-wise. And then-
Case wise is okay.
Right.
Because case wise is to prove
Okay.
that your thing is correct.
Okay.
Right?
Okay.
Now, ultimately, what should be the design you have to draw it, right? This is your base
Base unit.
unit.
Yes.
That you want to use it
Yes.
for it. So, this structure should be made available.
Okay.
Right? And you have to show that this structure really gives you the solid.
Okay.
So, for that, you have to give this.
Network.
Right? Okay.
So I'll
So,
put that
this
in
you
the
have
report.
to, in the report, you have to.
Okay.
write.
Good. Okay. So once the 5 sorter is done,
So, let us assume that this is working.
the 5 sorter. Yes. Sir. So now we'll use another unit which is
Because
3
if it
sorter.
does not work, then your everything is gone.
No, sir. All the cases are there, so that's fine. Report my cases we answer. I'll put the network also. So now we look at the 3 sorter. This is a very trivial design. Given 3 numbers, we just want to sort them, and we are saying that we can do them in 3 comparison and 2 phases. It is we just take any 2 numbers initially, and the third number we'll compare it with both of them. In fact, we could even
So
take
3
3 phases. We don't mind. And now what we are saying is we'll take the 5 sorter as one unit, 3 sorter as another unit, and even this sorting we'll do it in parallel.
Right.
Right?
So you get the 8 sorter.
Yes, sir. So 8 sorter, given 8 numbers, the first 5 go here, and next 3 go here.
Yes.
So beyond that, Abbas will talk about.
So up to this,
Yes,
you have spent 4 phases,
4 phases, sir.
right?
Yes, sir. 4 phases and 11 comparators we have, combining both.
So from now onwards,
Okay.
sir, for 8 sorter, we can use that improved 5 sorter and the 3 sorter, and this can be done in 4 phases and with 7 more comparators. We already are using 11 comparator here. For 5
For 3
sorter,
sorter,
we are
you made
using
3 phases.
yeah,
Right.
and 4 pages for 5 sorter. So they are in parallel. So overall there is 4 pages.
4
4
phases.
pages.
Now, I have one question. So why you are making 5 and 3? Why not 5 and 5? You get the...
No,
Next
we are
way it will become
in-
easier for us.
Okay. Well, I will come to that point later on. Sure.
So 8 plus 3 comparator for the previous phase, and for now there will be 7 comparators.
Merge, you have to
To
merge.
merge,
now.
we have to merge both. Yes. To merge, we have certain cases. Or if we have A, B, C, D, E, and X, Y, Z. For these are the 2 sorted sequences. To merge these, first we have to compare this with C. According to the result of this, we can, in the next step, either we have to compare this with this and this with this, or if it is greater than C, we have to compare this with this and this with this, and this with this. So without loss of generality, we can say that Y is smaller than C. In that case,
No, in that case, see, the way you are telling, I don't know how you are going to show in the form of network. You understood?
Correct. This is our basic unit, sir.
Okay, basically 5 and 3.
Yes, sir.
After that,
and
It's a merging one.
after merging, we
merging
use
also you have to give me the drawing.
Yes, sir.
So there may be a problem.
Yeah, merging will do.
दोनों का
Then we have to insert in ABC XY and in ABCDE CDE Z. This is the two cases. After this case that y is less than c, we have to compare y with b and x with a. And z can be inserted in 3 steps. First to compare with this, then if it is greater than this, we have to compare d, then with e. If it is smaller than c, we have to compare with b and then with a. So in 3 steps, z will be inserted. For this, there will be 4 cases. If x is less than a, if x is less than a, then it will be directly inserted here, and y will be less than b, then we have to compare one more with a so that we can know the exact position of y. Then we have this will be the x, y, a, b, c, d will be the sequence. If y is greater than this, then this will be the sequence. In the second case, if x is less than a, then it will be here, and y is greater than b, then y will be in this position. There will be no comparison in this case. Then there is a third case when x is greater than a. When x is greater than a, then we need one more comparison for x with b to insert either x here or here. And similarly the fourth case. So here we need one for the first comparison y with c, then 3 comparison for this to insert z, and 3 comparison to insert x, y. So total 7 comparison, and there are 4 phases. One phase for y to compare with c, and then remaining 3 for this and 3 for this. Those are in parallels. Overall, there are 8 phases in our 8 sorter and 8 comparison, and we have 24 comparison in bitonic, and in odd even 20 comparisons. We can use this 8 sorter as our basic.
No, but number of phases in bitonic?
7.
7?
No, for 8 sorter.
odd even uses 8 phases.
7.
Odd even.
7.
So what you are telling that your number of comparators should be less?
It is less, and
So
more
that
phase,
you
one
have
more
to
phase.
show me until unless
Network.
your diagram is
Yeah.
not there, I am not permanent, right?
Yes, sir. So we can use that 8 sorter as our basic unit for the network. Bitonic sorter. In bitonic sorting, if it is n elements, we use 2, 2, 2, then 4, then 8, and then 16. This way. So for till 8, we can use our 8 sorter, and in this way we can reduce the number of comparators by 3 and by 4. One of the examples.
3n by 4 comparators you are saying?
Yes, sir.
That is 1/4 of the total number of elements you are using?
1/4.
Are you sure?
Yes,
Go
sir.
back,
Yes,
go
sir.
back, go back, go back,
Yes, sir.
go back. You are using
Six,
18 comparators
in-
against 24.
Yeah,
Yes,
so
sir.
6
Six are
m in each 8 unit, we are saying. And
In each,
8 unit.
in
Sir, in bitonic, we are using log n plus 1 plus log n by 2 into n by 2. This many comparators in bitonic. We are,
try to understand. Your save is only base 8 sort
yes, sir.
8
Yes,
thing,
sir. Yes, sir.
right?
Yes, sir.
There you are using 18 comparators against 24.
Yes, sir.
Rest there is no change.
The rest is the same
There
as
is no
bitonic.
change.
Yes, sir.
Only this cluster.
Mm.
In that cluster, what is the total number of comparators you have?
Yeah, that I am writing. So this is total number of comparators in bitonic. We are reducing the first 6 phases till the 8. That we are reducing n by 2 into 6, and we are adding the number of comparators we are using from our base unit. That is n by 8 plus into 18. So this will be this will remain same, and this gives 3n by 4. This 3n by 4 after subtracting.
So like we have n over here, same byte,
And we are dividing this in 8
we
units.
will have n by 8 units. So in each unit we will replace whatever bytonic is doing by our 8 sorter. So we have n by 8 into 6 comparators at this side.
So
That means you are telling that 3n by 4 divided by n log square n is the actual percentage of
Yes,
yes, sir.
right?
Yes, yes, sir.
So that also you have to write. What is the
space.
ठीक है?
Yes, sir.
So for few things I am telling you. One is that you need the diagram, network diagram. Second thing is that you have to prove.
Yes. Case wise analysis is fine.
Case
Case
we have-
wise analysis,
we
okay,
have
but you have to theorem type you have to write.
Um,
Right, so like decision diagram, decision tree.
Okay.
You check this is there in 3 sorter or 5 sorter. There is a decision tree is there.
Yes, sir.
In any data structure will be
okay.
there.
So we'll make
So
it.
similar type of thing you have to do. Whatever you are making case wise, that is in terms of tree.
Alright.
If A is less than B, then what you can like that. Otherwise, you, right?
And this percentage.
Percentage is required. Want to show anything else?
No, sir.
No, sir.
Any questions? So diagram is required.
Are you taking the same number of phases or?
No. Overall, we are using 2 phases extra. But we'll be saving 3n by 4 comparators,
And
but we'll be using 2 phases.
Time is increasing by 2.
In that 8 sorter part, we're using 2 more, and that's all. Nowhere else special.
So you find out also complexity, cost and other things.
Yes, sir.
Good morning to all of you. Our problem is parallel approaches to compute DNA sequence alignment. This is the outline of our work. First of all, the problem is DNA sequence alignment, so we need to understand basically what is the DNA and how it is important to align two DNA sequence. So first of all, DNA holds a vast library describing how a cell works, and basically DNA are the molecular codes for the genes. So DNA consists of 4 types of nucleotides: A, T, G and C. So from our problem point of view, we need to understand that basically DNA is nothing but the sequence of these 4 types of nucleotides. So this is the motivation for this problem. Basically, whenever a new gene is found, there is no idea about the functionality of that particular gene. So what we do, we try to infer the functionality of that particular gene with the help of the existing genes whose functionality we already know. So basically what we try to align that particular genome or DNA sequence with the existing sequence, and whatever the matching in between that particular in these 2 DNA sequence, on the basis of that we try to define the functionality of that particular gene. Now, what are the challenges in DNA sequence alignment? Basically, in DNA sequences there are a thing which is called mutation. Basically, what happens is some nucleotides keep around changing in one another. So basically, this mutation doesn't affect the functionality of the DNA molecules. Like suppose there are some nucleotides which change into some other nucleotides. So basically, the functionality remains the same. So many times we don't need the exact match, and this different this DNA sequence may have the same type of functionality. So first of all, from the technical point of view, we are going to define a distance matrix. So to define proximity between 2 sequences, we need a distance matrix. Basically, we are going to align 2 sequences. So we need some kind of measurement to measure how close those 2 strings with each other. So if we are going to consider the Hamming distance, so the problem with Hamming distance is that the ith letter of first string is compared with the ith letter of the second string. So you can just see, if we are going to compare these 2 strings, the Hamming distance is not a very good idea to compare these two strings. But if we simply make a one shift to one string, you can see these two strings are almost the similar. So here the concept of edit operations. What we are trying to calculate the edit distance rather than the Hamming distance. So basically there are four types of things in the edit operations. First is match, mismatch, deletion and insertion. You can see whenever the two characters in the string are going to match, this is called a match. Here you can see this is a mismatch, this operation going to represent the deletion, and this is the insertion. These are edit operations, and basically edit distance is nothing but it is the number of edit operation required to transfer one string into the another string. Now basically what the problem is, it is basically the optimization problem. The sequence alignment problem is find such an alignment which uses the minimum number of edit operations. You want to convert one sequence into another sequence, and you want to optimize the number of edit operations. Optimize in the sense you want minimum number of edit operations. The other flavor of the same problem is that whenever you align two sequences, and whenever a match occurs, you assign some score to that particular match and penalty for the mismatch. So corresponding to the alignment, we have a matching score and we have to maximize this score.
Now, why string matching algorithms cannot be used? Actually, string matching algorithms take up a pattern and try to search for that pattern in the given text. It tries to find the exact match. But here what we want is that we want a score which corresponds to the matches and insertions and deletions. So we can't use the string matching algorithms, the standard string matching algorithm. So here what we have is a dynamic programming solution. The entry, we form a alignment matrix. Here is the first sequence, the second sequence. Any entry ij, gij is the optimal alignment from beginning from 0, 0 to up till ij. That is an optimal path from this starting cell to this cell. And the recurrence is defined as either the max of gi minus 1, g minus 1 plus delta if there is a match in ai or bj. Otherwise, what we do is that either we come from this place or we come from this place. That these two positions correspond to insertions and deletions, and for them we impose a penalty, that is sigma. So what we have is this sort of dynamic programming matrix. This is the case of longest common subsequence, which is a sub problem of special case, you can say, of sequence alignment. So we just form this matrix and fill up these values, and then we from this last cell we have to trace back to find the optimal alignment. The computational expenses here are the time required is order n square, because we have to fill up this n square matrix with the size n cross n, and the space required is also n square. But the problem is that DNA sequences are so large that it is not feasible to align using the n square space, and so we use the linear space alignment algorithm. Here what we do is that we observe that there is a dependency that for calculating this cell we need the values of only these three cells. We don't need any other values. So what we do is that we start calculating our values in this fashion. That means we calculate first this column, then we calculate all the values of this column. For example, if we have to calculate this value, we have to just use 3 values. Now when we are done with these 2 columns and we begin this column, we don't need the values of this column, because all these values are dependent on these values. So we can just free this space and calculate this column. And so progressing in this fashion, we calculate the score up till here. And then what we have to do is that now since we have used only this is just 2 columns linear space, so to find the alignment, actual alignment, we have to again in the traceback phase, we have to again fill up these cells as we move from this column to the first column. So this is the linear space approach.
Now the parallel approach. Basically, as you can see, a particular value is dependent on the its 3 neighbors. So there can be a wavefront parallelism in this particular approach. So basically, what we try, the basic approach is that suppose we have a preprocessor. So you can assign the diagonal in this fashion, like p rows, diagonally p rows, and you can calculate all these values. When suppose in this particular iteration, this processor is now free, so you can assign this processor to this particular row. So this value and this value both calculated in this next step, and similarly if in next step, so you can calculate in this particular fashion. So basically this is the basic funda of that particular approach. Now what here we are doing, that we are dividing the whole matrix into a number of blocks. Here a particular block contains a number of subsequence of that particular string. Now we are calculating a particular block in diagonal fashion. In the similar fashion we just shown, we are calculating with the help of wavefront parallelism. So here's the analysis of that particular approach. Suppose we are breaking the matrix into the blocks of n by k cross n by k. Now suppose we have p processor, so we can calculate the score value of p cross k submatrix in the k steps using the wavefront parallelism.
Actually what we are doing is that here these are actually the blocks, not the individual cells. So if we have p processors, what we can do is that using this type of parallelism, first we calculate this submatrix of p cross k. In the first step, we use only one processor. Here we are assuming we are having 3 processors. In the second step, we can use 2 processors. In the third step, this is the third step, we can use 3 processors, and we can go on in this fashion up till we reach this point. And here, when we are using only 2 processors, what we can do is we can assign the third processor to this point. So in one phase, what we can assume is that we are calculating p cross k submatrix.
So yes, when we are going to compute the p cross k submatrix, the total time complexity will be k by p, because we will have k by
k steps in
k by p submatrix, and each submatrix will take k steps. So into k plus if k mod p is not equal to 0, then we need some extra k steps, and finally we need p steps when here for the last particular case. And suppose t is the time taken to calculate the values of one particular block, so we simply multiply it with the t. So this is the total time complexity. Now if we are taking the
because we are using the dynamic programming, usual dynamic programming matrix, so aligning n cross k into n cross k takes n square upon k square time. So multiplying it t, we get.
So here's the total time complexity. If we are taking log n processor, the time complexity is order of n square by log n. And if we are going to calculate the cost, it is order of n square. So it is cost optimal.
Now what we in this what we see is that we can't do anything regarding this part, because there is a dependency that for calculating this block we need the values of these 3 blocks. So the 4 Russian approach, what it tries to do is that it tries to somehow minimize this value of t, that is the calculation for one single block. Now how this is done, actually this is just for a special case of LCS, which is a special case of sequence alignment. Now in LCS what we observe is that whatever penalties we were imposing, this delta is 1 and this sigma is 0. So what happens is that if you take consider this as a block, so you for calculating the values of a block, what you need is that inside this there are small cells. This is a block. So what you need is that these values and these values for calculating this block. Now what happens is that since the penalty the score awarded is 1 and the penalty is 0, so these values will only differ by 1 or 0. So what we can do is that if we are giving the cornermost value, we can represent this as a bit string 0 1 1 0. Now for a block of dimension k dash cross k dash, the possible combinations of binary values is 2 to the power k dash cross 2 to the power k dash for all these bit strings. And for all these, whatever we are aligning, this sequence and this sequence, this is of length k dash and this is of length k dash, and since the alphabet is 4, ACTG, so the maximum possible combination are 4 to the power k dash into 4 to the power k dash. So the total possible combinations are 2 to the power k dash into, this gives us 2 to the power 6 k dash. So for one block, how many possible configurations are possible is equal to 2 to the power 6 k dash. So what we, if in the case when k dash is equal to log n by 6, then this total number becomes linear. So what we do is that we pre-compute all these possible blocks and we make a table of size n because this is linear. And now instead of when we are actually calculating the values of this block, but now what we have to do is that we just have to look up in this table because we have pre-computed this table, and this lookup takes only log n time. So instead, in the previous case, it was taking n square by k square time. Now we have to just look up into the table, and that time for computing this table is n square by log square. N into log square n for sequential, and we parallelize it to so we got n cross log n time using log n processor. So now the time for computing alignment is becomes n square by log square n, and total time becomes n square by log square n plus n log n. This is for time of pre-computing the table. So the cost is n square upon log n.
No, my point is that just prior to that you told that it is cost optimal if it is order n square.
Sir, this is both are the different algorithms.
Whatever
Both are
it is,
two different.
an algorithm is cost optimal if it matches with the lower bound.
So actually,
for
the sequence alignment till now, no lower bound has been proved.
So
For example, in the
you cannot tell it is a cost optimal, right? You can tell that it is efficient algorithm, right? All those.
So this is the 4 ration speed up. So using the parallel approach, this is the best we got. That is n square. If this factor is greater than it's of order of n square by log square n, wherein previously we were getting n square by log n. Now, due to this constraint, there are not many options for deterministically doing some new parallelism. So what we do is that we use some techniques for achieving more speed up. Now, for that, what we do is that we define a threshold value that up till some consecutive blocks, if we have we have got our score more than actually we have to model the problem in opposite way. The score is such that if the score is more, that means that two sequences are more far apart. It's just the positive and negative are changed in the penalties. So if this alignment up to here exceeds certain score, then what we say is that we can't have our path passing through these blocks, because the theory behind is that if you reach up till this block and you have some alignment score, and from this time from this place, what best you can have is that you align all the possible part of sequence left, but still that sum of this alignment and this score will give you a very bad value. So that is so that means what we do is that if we reach this threshold value, we do not have to calculate all these values below this, because no path can come like this and go, because always you have to align in this fashion. And similarly, if you see over here, if you exceed the values in these blocks, then you don't have to calculate the values of these two. The path can pass on like this. So when we are doing this parallelly, what we do is that if we are having the kth wavefront, this is the kth wavefront, and we observe the values of the edges of values of the k-1 and k-2th wavefront. So if here the values exceed beyond, we have to find a row j where the values of blocks exceed the threshold. So if this exceeds the threshold, we don't have to calculate all these values, and now our matrix reduces to this much part only. And similarly in this case, if this is k, then if these two blocks of k-1 and k-2 have more than this value, then we don't have to calculate all these values further, because all this this area will be neglected and the path will pass on like this. So this is one speed up, but the thing is that all these approaches are sort of improvisations. They don't give you a improvement by a factor of by some order. Then there is another approach of using forward and backward recurrence. Here what we were doing was that it was Gij denoted the optimal alignment from starting from the 00 cell to the ij cell. The backward recurrence calculates the values starting from the last cell, and Fij means the optimal alignment from this from n, n to ij. Now what we do is that we divide our matrix into two parts. The first part is calculated using the forward recurrence. The second part is calculated using the backward recurrence. Both can be done using the linear space. Now we take the middle column and calculate the sum of values of Gij and Fij. Now the optimal path will always pass through that cell where Fij plus Gij is maximum. So what we do is that we have found the cell in this column through which the path will pass on. So now what we can do is that once we have found this, so we can divide our problem into two parts. Since this is the optimal alignment up till here and this is the optimal alignment up till here, now we can forget these blocks because the alignment will always pass through this. And actually we are doing it using linear space, so we only have score up till here. Now we have to again trace back and again calculate these values. So in each step what we do is that we speed up by a factor of half. But this also doesn't give us a improvement in order. Further, there are some approaches, but for example you can see over here that the path in the traceback phase, we see that the path is passing through these values. Now if we know that the path has reached up to this cell, then obviously we don't have to again calculate in parallel this block, because the path will never pass through this block. So what we can do is we don't have to calculate this path, block. We can instead calculate in some other blocks, storing the values of this. I'll show in the next PPT. And we also don't have to calculate the values for these cells, because the path will never pass through this portion. So what we do is that we save these values along the borders, this and this of each block. So these are two nk values. If k is log n, then we are using n log n space now. And what we do is that in this case, instead of calculating value of this block, since we have all the border values, we can calculate whatever block we require for our optimal path. So now the main constraint what we observed was that for calculating each block, the values of adjacent 3 blocks is required. So this is the main constraint in going through in calculating the value using a deterministic algorithm which gives you a correct exact optimal score. So the solution is that we have to have algorithms which gives us the approximate scores, and these algorithms are based on heuristics. These algorithms, what they do is that when we are searching for a gene in a huge database, we have to filter out those genes which are highly dissimilar than the query gene. So these algorithms are used here. And the first, the basic approach which we consider, and then we base our randomized algorithm on this approach. What we do is that we take k size substrings which gives exact match in 2 sequences. For example, a k exact match, k size exact match can occur here, all these places. And now what we say is that the optimal path will pass through some of these k exact matches. So here what we do is that the steps are that first we have to find substrings of length k which gives us exact matches. Then we have to find the longest common subsequence of matches. If these are 2 sequences, then the same k substring can be over here, here and here. So we can have something like cross matches. So we have to avoid these cross matches. So what we do is that we save the positional information of this. And once we, for example, if we name it like number 1, and this is also corresponding 1-to-1 matches, 2. So now we have to form a longest common subsequence of matches. So this is done just to avoid these cross matches. Now once this is done, what we do is that we have something like this. This is the whole sequence, and in some parts we have k exact matches, like this. Now these are exact matches, and between these we have gaps, and we use the standard dynamic programming algorithm to calculate these gaps. And now we will present the randomized approach, which is somewhat based.
Basically, we see lots of algorithms, lots of improvements through which we can improve the running time of particular algorithm, but that improvement is not of some particular order. So what in randomized approach, what we are trying to do, we are trying to find some approximate score, but with some lower time bounds. Basically, the idea for this approach we got from the paper presented by Rajashekharan. In his paper, what he showed, he
Rajashekharan is a string machine program.
Pardon?
It is a string machine program, right? Rajashekharan is for.
No, for sequence analysis. What he did, he take a random number particular, and he took a string of length n to the power epsilon, and once again he took the same position in the second particular string, and he took n to the power epsilon length string from this substring from this string also, and he tried to align these two particular strings.